Welcome everybody in section 7.3 of AB Chemistry series. Today we will talk about reaction, quotient, and equilibrium constant. In the previous videos, we talked about the equilibrium constants. We talked about the equilibrium reactions, which the rate of forward reaction is the same as the rate of the reverse reaction. Since we have products and reactants in a certain point of equilibrium, if I ask you, can I determine the ratio between the products and reactants? Do I have more products? Do I have more reactants? Or they're equal? So how can I represent this thing? There is a beautiful concept that is called Kc, as we can see. The Kc represent a ratio of the products over reactants. So let's have a look at these things. We will introduce you to the equilibrium constant, and the equilibrium constant is represented in letter K with the small c. So the small c represents or stands for a concentration, and the K is the equilibrium constant. Kc is equal to the concentration of the products over the concentration of reactant. But if you look at this equation in here, you can see that the coefficients of products, the coefficients of reactants are changed into powers of the concentrations. And the expression of Kc represents the concentration, as we said, and they are represented in terms of square brackets. So once you find square brackets, then you're dealing with concentrations. It's not the only thing that you have to cover. There's a beautiful and important rule says if your reactants or products contains a solid state thing or liquid, pure liquid, then we do not put them in the expression at all. The only guys that we include them in our expressions of Kc's are only gaseous and aqueous. Aqueous at that point means like they're mixed with water. Now, how can I solve this beautiful example above? The question says, write the equilibrium expression Kc for the following reactions. All right, so first of all, you have to check. Do I have gaseous or aqueous? Okay, it works, it works. Now I have to say, okay, the Kc is equal to products of reactants. The products are oxygen. So we have to put them in a square bracket. We put O2. And since the oxygen is multiplied by 3, you can see this is a coefficient, then it's raised to the power 3. And then you put it over. What is your reactant? The reactant is O3, which is ozone. This gas is responsible on protecting us from the UV lights that comes from the sun. We have O3, the O3 is multiplied by 2, then it's raised to the power 2. Do not forget to put them in square brackets. And you have to make sure that these are in a gaseous or aqueous states, then our expression is ready. And now let's cover the second one. Okay, first of all, check the states, gaseous, gaseous, gaseous. Now everybody's happy. I have to put products of reactants. It's gonna be, what is your product? We open a square bracket, we put square bracket NOCl, we close it, it's multiplied by coefficient 2, then it's raised to the power 2 over, okay, you have two reactants, you have Cl2, you put it in square bracket, it's not multiplied by anything, then it's raised to the power 1, and then you say multiplying, you have NO to the power 2, then I have to say this is NO, is it NO2? It's NO, and it's raised to the power 2. So this is the second expression of Kc for this reaction. Now let's go to the last one here. First of all, check the states. It's in aqueous, aqueous, aqueous. Okay, everybody's happy. It's Kc equals to the concentration of Ag of NH3. Okay, positive. Okay, close the bracket. It's not multiplied by anything. It's only 1 over NH3 in NH3 in aqueous form, multiplied by the Ag positive. Okay, So this is the expression of Kc for this reaction. Okay, but you have to keep in mind, not all of your reactions contain only aqueous and gaseous. Sometimes you have solids, sometimes you have liquids. So how can I deal with these guys? Now let's have this one here. So first of all, we have to look at this reaction. You can see that this is a liquid state. We don't need it. This is gaseous. Yeah, sure, I need it. So I have to say Kc is equal to CO. I need it. And if you don't like to make several mistakes, you can say, okay, the guys that are in a liquid or in a solid state, we just put them one instead. So it's going to be multiplied by 1 over. You have hydrogen, it's a gas. Okay, it's acceptable. I have to put hydrogen and then multiply by. This is a gas, then it's going to be CO2. After doing this process, it's going to be CO over H2. Do not forget that the sign between the two species here is multiplication. It's not a summation process. And then it's CO2. So this is the expression of Kc for this reaction that contains water that is in a liquid state that is excluded from your reaction. Now let's go to B. Okay. Um, okay, first of all, check the states. Acceptable. No, it's not. It's acceptable. It's not. So first of all, I have to say, you have CO2, okay, just like for Kc, is equal to CO2. Do not forget the square brackets for Kc's. Square brackets represent concentration. We close it, it's multiplied by 2. I have to say 2. Okay, since this is a solid, I can say like, okay, it's multiplied by 1 over, okay, the SnO2, this guy in here is also excluded, so we put 1 instead, and then we say multiply by CO, which is the needed guy. We put CO to the power 2, and then it becomes CO2 to the power 2 over CO to the power 2. So this is the expression of Kc. So we have another type of equilibrium constant that is represented in terms of Kp. And from Kp, since K represents the equilibrium constant, then the small p here represents the pressure. Okay, so at equilibrium, you have to keep in mind the pressure becomes constant. So we're gonna do the same thing, like we have the ratio of the products over ratio of reactants, and keep in mind the small p's here represents the partial pressure of each gas. You just notice that. For example, if you have the P total, it equals to the partial pressure of gas 1, partial pressure of gas 2, partial pressure of gas 3, etc., etc. Okay, so what's meaning of partial pressure? It's the amount of the pressure that is produced from a single species. Now, guys, pause the video and read this example carefully. Okay, as we can see, we have a gaseous system that is composed of three gases: nitrogen, hydrogen, and ammonia gas. All of these gases have partial pressures. The pressure that is exerted only from nitrogen molecules is called the partial pressure of nitrogen gas. And the same thing for hydrogen, same thing for ammonia. Now, if I want to describe or to write the expression of the Kp, the Kp value represents, or you should write, the partial pressure of a products over the partial pressure of reactants. So product here is ammonia. You have to say P, you write an H3. Do not forget that the coefficient of the gas becomes as a power, and you have to divide it over the multiplications of the pressures of reactants. So we have reactant hydrogen, reactant nitrogen. So it's going to be the partial pressure of hydrogen gas by power 3 multiplied by the partial pressure of nitrogen gas. So this is the expression of Kp. And keep in mind, since you're dealing with Kp, which means a pressure, then the products and reactants must be in a gaseous state. Do not accept the aqueous form in Kp because aqueous is not a gas. So this is the expression of Kp. Now, if you want to substitute the values of the partial pressure of ammonia, the partial pressure of hydrogen, you can see down below. These are the pressures that are given in the question. So you have to substitute them carefully. We have to start solving these questions. You can pause the video and test your knowledge. The question says, consider the following equilibrium. The equilibrium constant expression is, okay, you have to check the states first. It's acceptable, acceptable, it's not acceptable. Then the value of Kc is equal to, you have a product CH4, okay, it's multiplied by coefficient 1, it's raised to the power 1 over the concentration of H2 that is raised to the power 2. So, do we have any answer that looks like our answer in here? Yes. This is not true because the hydrogen is not raised to the power. Then it's not acceptable. The second one you can see, yeah, it's the same as our answer. Then this is the true one. The one in here, he included the C that is in a solid state and we don't put it at all. The last one is including the C2, which is also not acceptable. So the answer in this case is B. Let's go to the next one. Pause the video and read the question carefully. Given the following equilibrium system, here it is. What is the equilibrium constant expression for the system above? Since this is a liquid, then we did not include it in our system. And this guy here is included. Then the Kc is equal to, we have to put 1 because this is a liquid, divided over the concentration of Br2. So which of these answers represents the answers that we got? The first one, he included the liquid state. No, it's not acceptable. The second one, he put only Br2, but Br2 is in a reactant side, and this is not true. C is true because he put 1 instead of a product that is in a liquid state, and then this is for sure, this is a true answer. This one here is not a true. This is completely wrong expression. Pause the video and read it carefully. For each of the equation below, write the expression Kp. Kp only takes the gaseous species. So this is a gaseous, this is a gaseous, and this is a gaseous. Then I have to say, okay, the Kp is equal to the partial pressure of Cl2, okay, multiplied by the partial pressure of the SO2, okay, over the partial pressure of SO2 Cl2. Do not forget to put the P's, the partial pressure for all reactants and products, if they are in a gaseous state. Let's write the Kp for this reaction. First of all, you have to look at the gaseous. This is gaseous. Okay, okay. No, it's not okay. So you have to say, right, the products are equal to, you have water, then you have to say the partial pressure of H2O to the power 6, okay, because the coefficient of water is 6, multiply, do not put a summation process, multiply that by the partial pressure of CO2 to the power 6 and divided by the partial pressure of O2 to the power 6. And since this guy here is in a solid state, then we put multiplying by 1, and at the end, it's like this. So far, I will stop here. We complete part 2 of section 7.3 next time. If you have any questions, you can ask me in the comments below. Have a nice day.